Welcome to my video, Hooke's Law Explained, the physics of springs and elasticity. What is Hooke's Law? Hooke's Law describes how an elastic object like a spring responds to a force that tries to stretch or compress it. The law states that the force needed to extend or compress a spring by some distance is directly proportional to that distance. So in this case, we have a spring that's just sitting there, nothing on it yet. And then we add a weight to it, it extends x distance. We add two weights, it extends 2x. So that's directly proportional. So if we write Hooke's law in mathematical forms, we get the force is equal to minus some constant k, which is a spring constant, times the displacement x. So the force is equal to the force applied to the spring, and that's going to be in units of newtons. The spring constant is going to be the stiffness of the spring. It has units of newtons per meter, and x is going to be the displacement from the spring's resting position in meters. So we have three basic cases here. One is where we're trying to stretch the spring. X is greater than 0. The spring exerts a force back to pull it back. This is the case where the spring is just sitting there in equilibrium. And then this is the case where we're trying to compress the spring, but the spring exerts a force out to decompress it. So the spring always moves opposite of what we're trying to do. Let's look at a numerical example. Pull on a spring so that it stretches 0.2 meters, and the spring constant is 100 Newton meters. So in Hooke's law, the force is equal to minus kx, and the force here is minus 100 times 0.2, which is minus 200 newtons. So that's our net force required to extend the spring with a spring constant of 100 newtons per meter, 0.2 meter. So this means that a spring exerts a force of 200 newtons backwards, trying to return the spring to its original length. Another example, if a spring stretches 0.05 meter under a force of 10 newtons, find the spring constant using the rearranged formula. So in this case, we're going to divide the F is equal to minus kx divided by both sides by x. So we're going to k is equal to F divided by x. We're not worried about the minus sign here because the spring constant is always positive. And so in this case, the force is 10 and the distance is 0.05 meters. So our spring constant is 200 Newton meters. One thing we have to be aware of is we can overstretch the spring beyond its elastic limit. So if we stretch the spring too far, it won't return to its original shape. It will be permanently deformed. When this happens, the material goes beyond its elastic range, and here's what's called the plastic range. There, it's no longer a useful spring. It doesn't obey Hooke's law. One example of this would be like a ballpoint pen. If you take the spring out and you stretch it too far or use the pen too much, the spring loses its springiness, if you want to say that. It's no longer functioning in the elastic region. It's not useful anymore as a spring. So here's an example. This is a slinky toy that a lot of kids have, or I used to have one a long time ago. And so the spring constant here is 0.5 to 1 Newton per meter. Now if we look at a more stiff spring, like on a trampoline, where people can bounce up and down, here the spring constant is approximately 4,500 newtons per meter. It depends on the trampoline and how it's made, but that's the range we're getting. It's much larger than that of a slinky. That's the message. Now, in the suspension of a truck or a car, you've got this big old heavy spring right here. And this is actually from my Chevy Silverado 1500 truck. And so there the spring constant is approximately 130,000, so it's much higher because you're supporting all the weight of the truck and whatever you're hauling in the truck. So it has to be a big heavy spring that's in newtons per meter. So kind of in summary, looking at some of the limitations of Hooke's law, it's a linear model that works only within a specific range. It does not account for metal fatigue. As we showed the example of the ballpoint pen, where you constantly are using it, the spring can weaken by repeated use. Metal does fatigue over time, And the temperature range, if it's too hot or too cold, it will get out of the elastic limits and not function properly. And then if you have some kind of complex deformation, many materials are anisotropic, they work in different directions. So you need to take that into account. Hooke's law is a linear approximation over a certain region. I want to thank you for watching this video. Hope you liked it. If you did, give me a thumbs up, subscribe to my channel, and there's additional information about Hooke's law in the description of the video. Once again, thank you for watching.